Step right up, folks. Behold the wackiest and most thrilling ride you'll ever see. Welcome to the TCA cycle at Sketchyland.
Damas y caballeros, por favor mantengan sus brazos y manos dentro del viaje y no tomen fotos.
In this sketch, we'll talk about the TCA cycle. The TCA, or Krebs cycle, is a series of chemical reactions that are necessary for aerobic metabolism and ATP synthesis. The TCA cycle takes place in the mitochondria, and that's why this ride sits on a mitochondria-looking platform. To recap, 1 glucose produces 2 pyruvate, 2 NADH, and 2 ATP during glycolysis. When oxygen is available, pyruvate enters the mitochondrial matrix and is converted to acetyl-CoA via pyruvate dehydrogenase complex. This step produces an additional 2 NADH. Now we're left with 2 acetyl-CoA molecules, which will enter the TCA cycle. The TCA cycle produces 3 NADH, 1 FADH2, 2 CO2, and 1 GTP, or 1 ATP, from 1 acetyl-CoA. This convenient snack stand will help you remember the products of the TCA cycle. To the left, we start with 1 acetyl-CoA. Acetyl cola. To the right of the checkout arrow, we have 3 thirst-quenching NADH energy drinks, 1 FADH energy bar, and a triplicate of G brand batteries. You'll also see 2 areas of black carbon dioxide smoke. Pop quiz! How much ATP is made during the TCA cycle if we start with 1 acetyl-CoA? Pause the sketch if you need some time. Okay, welcome back. The snack stand sells NADH drinks for $2.50 and FADH2 bars for $1.50. Just like how 1 NADH will produce 2.5 ATP and 1 FADH2 will make 1.5 ATP during the electron transport chain and oxidative phosphorylation. The TCA cycle produces 3 NADH, 1 FADH2, and 1 GTP, or ATP, per 1 acetyl-CoA. So let's do the math. 3 times 2.5 plus 1 times 1.5 plus 1 equals 10 ATP. 1 acetyl-CoA produces 10 ATP. Now let's talk about each step in the TCA cycle. The best way to remember each step is to count the number of carbons. In this sketch, we'll use people to represent the number of carbons. In step 1, citrate synthase combines 2 carbon acetyl-CoA and 4 carbon oxaloacetate to make 6 carbon citrate. You'll see a young couple patiently waiting to get on the ride. One of them is holding a bottle of acetyl cola. They represent acetyl-CoA, which has 2 carbons, hence 2 people. I bet they want to get on that Oaxacan hot chocolate cup. Oxaloacetate, that is. Citrate is the first intermediate produced during the TCA cycle. Citrate sounds like citrus, so of course we've included a cup of orange juice. And what classically goes well with OJ? 6 people, of course. The enzyme that synthesizes citrate is citrate synthase. This is represented by a cast member fixing that orange juice cup. Keep in mind that he's using a screwdriver. This will be important and we'll talk about it soon. Interestingly enough, ATP inhibits citrate synthase. High ATP inside cells slows down the TCA cycle because we have plenty of fuel available and don't need to make more fuel. Unfortunately, this pesky ATP-powered animatronic seagull escaped the pyruvates of the Caribbean ride and is trying to attack our cast member. When there's plenty of fuel available, the TCA cycle is often backed up. Excess citrate leaks into the cytosol to inhibit PFK1 and slow glycolysis. You'll see a large acorn tree right behind the group of riders sitting in the OJ cup. An acorn has fallen just between these riders and our next group sitting in iced OJ. Aconitase, isomerizes 6-carbon citrate to 6-carbon isocitrate, which is represented by iced OJ. In step 3, isocitrate dehydrogenase will oxidize 6-carbon isocitrate to 5-carbon alpha-ketoglutarate. We've included another hardworking cast member who's cleaning up some spilled ice OJ. No bueno. This guy is isocitrate dehydrogenase, and he's got a towel just like all our dehydrogenases. There's an NADH drink and some black smoke, so you'll remember that this rate-determining step produces 1 NADH and 1 carbon dioxide. We've got 5 frat bros in the next group who belong to the Alpha Kappa Gamma fraternity and represent alpha-ketoglutarate. Time to rage. Check it. How many frat bros does it take to screw in a light bulb? None, because it's already lit. All right, let's get back to the cast member. Poor guy is just not having a good day. You'll see another ATP-powered seagull trying to attack him. That's because ATP inhibits isocitrate dehydrogenase the same way it inhibits citrate synthase. If there's plenty of fuel available, the ratio of ATP over ADP will be high, and we can slow down energy production by shutting down the TCA cycle. Just like ATP, when NADH levels are high, there's a lot of energy inside cells, so we can slow down energy production by slowing down isocitrate dehydrogenase and the TCA cycle. In contrast, if cells are running low in fuel, most ATP has been used up and there'll be more ADP, which will stimulate the TCA cycle. In step 4, 5-carbon alpha-ketoglutarate is transformed into 4-carbon succinyl-CoA via alpha-ketoglutarate dehydrogenase. You'll notice a wet towel on the floor next to some spilled cheap beer, which will represent alpha-ketoglutarate dehydrogenase. I wonder where's the cast member? This oxidative decarboxylation reaction produces 1 NADH and 1 carbon dioxide, again represented with the NADH drink and black smoke. Alpha-ketoglutarate dehydrogenase uses TPP, NAD+, FAD, lipoic acid, and CoA as cofactors, just like pyruvate dehydrogenase. If you don't remember anything about pyruvate dehydrogenase, please watch the PDC sketch. Our product in step 4 is succinyl-CoA, and our next group of 4 people are sitting in a cola cup with a straw, which is used for sucking cola, or succinyl-CoA. Ah, shucks. Another pesky ATP-powered seagull, but this time it's grabbing that beer-soaked towel, kinda like how ATP shuts down alpha-ketoglutarate dehydrogenase. NADH also inhibits alpha-ketoglutarate dehydrogenase the same way ATP does. Succinyl-CoA also inhibits alpha-ketoglutarate dehydrogenase, but through product inhibition. We're more than halfway done. Let's get to the next step. You'll see another cast member, but this one is using a power drill to fix the cola cup. This person is succinyl-CoA synthetase. Remember our citrate synthase cast member who was using a screwdriver earlier in the sketch? In general, synthase enzymes don't require or produce energy in the form of ATP or GTP, while synthetase enzymes do. That's why the succinyl-CoA synthetase cast member is using a power drill. This reaction produces 1 GTP or ATP, but for the purpose of this sketch, we'll include a triplicate of green G-brand phosphate batteries. In step 5, succinyl-CoA synthetase transforms 4-carbon succinyl-CoA to 4-carbon succinate. Our next group of 4 writers are sitting in lemonade, or what I like to call succinate. It's like lemonade, but it sucks a lot more. You'll see another wet towel on the floor next to the group soaked with succinate. Ugh, this ride can get very messy, as you can see. This particular towel is succinate dehydrogenase. In step 6, succinate dehydrogenase turns 4-carbon succinate into 4-carbon fumarate. We've got another foursome of writers sitting in a fuming teacup. Let's hope they make it out alive. This step produces our first and only FADH2, which is short for flavin adenine dinucleotide, and comes from riboflavin. You'll encounter an FADH energy bar nearby, which costs $1.50, and coincidentally provides 1.5 ATP during the electron transport chain and oxidative phosphorylation. Succinate dehydrogenase is found in the inner mitochondrial membrane, unlike all the other enzymes in the TCA cycle, which are found in the matrix. Next to our fuming fumarase cup, there's a cast member taking a smoke break. He's probably had enough of the spills and killer seagulls. He's fumarase, which hydrolyzes 4-carbon fumarate into 4-carbon malate. He better watch out for that malfunctioning teacup spinning out of control, though. Malfunctioning for malate, that is. I am very concerned for these writers. But, oh well. Hold on to your pants, guys. We're almost done. We finally encountered our last towel and dehydrogenase. You'll also see a puddle of tea next to the malfunctioning malate cup. In the last step, malate dehydrogenase oxidizes 4-carbon malate into 4-carbon oxaloacetate. We've reached the Oaxacan hot chocolate cup once again. Viva Oaxaca! We produce one NADH during this step, as represented by the flying NADH drink. Just a side note for malate dehydrogenase. This enzyme is part of the malate aspartate shuttle, which is used to transport electrons produced during glycolysis across the mitochondrial membrane for the electron transport chain. We'll talk about that in the electron transport chain sketch. Finally, oxaloacetate combines with acetyl-CoA just like we talked about in step 1, and the cycle repeats. We'll conclude this sketch with our patented stop-ride switch. You'll see a big bottle of NADH pushing that big red stop button. As we briefly mentioned earlier, high NADH to NAD+ ratios slow down the TCA cycle. Just like ATP, when NADH levels are high, there's a lot of energy inside cells, so we can slow down energy production by slowing down the TCA cycle. I hope that didn't make your head spin. Well, don't worry, because I'll quickly recap what we just talked about. The TCA cycle is a series of chemical reactions that take place in the mitochondria and are necessary for aerobic metabolism. The TCA cycle produces 3 NADH, 1 FADH2, and 1 GTP, or ATP, for every 1 acetyl-CoA. We started with 2 acetyl-CoA, which combines with oxaloacetate to make citrate via citrate synthase. ATP inhibits citrate synthase. Next, aconitase isomerizes citrate into isocitrate. Then, isocitrate dehydrogenase oxidizes isocitrate into alpha-ketoglutarate and produces 1 NADH and 1 carbon dioxide. ATP inhibits isocitrate dehydrogenase, while ADP activates isocitrate dehydrogenase. In step 4, alpha-ketoglutarate dehydrogenase oxidizes alpha-ketoglutarate into succinyl-CoA and produces 1 NADH and 1 carbon dioxide. ATP, NADH, and succinyl-CoA inhibit alpha-ketoglutarate dehydrogenase. In step 5, succinyl-CoA synthetase synthesizes 1 GTP, or ATP, while turning succinyl-CoA into succinate. In step 6, succinate dehydrogenase turns succinate into fumarate, and we produce our first and only FADH2. In step 7, fumarase hydrolyzes fumarate into malate. In step 8, malate is oxidized into oxaloacetate via malate dehydrogenase to make our third and final NADH. Finally, NADH inhibits TCA cycle reactions. And there you have it. You've mastered the TCA cycle. That wasn't so bad, right?